During the 1980s, with an eye towards the future and the ever-increasing sophistication of software, arguably some of the most groundbreaking innovations within CPU design occurred. Processor evolution during this decade formed a technological bridge, connecting the primitive beginnings of computing with the rich, complex experience that envelop our lives today. Take a look at any computing device used today. From $100 million supercomputers to smartphones, they all share a common, powerful characteristic: multitasking. Multitasking allows multiple programmatic tasks called processes to efficiently run concurrently across even a single CPU. During the 1960s into the 1970s, the multitasking paradigm was gaining traction in the mainframe world. Initially, the concept was implemented in a cruder form known as multiprogramming. Multiprogramming was accomplished by processing programs in batches, jumping between them during regions of code that wait for hardware input. This would eventually evolve into time sharing, in which hopping between processes happened in real time, allowing each program's CPU access until it needed to wait for external I/O. IBM's System 360's operating system was a notable example of this evolution. By the late 1960s, true multitasking started to emerge in operating systems such as DEC's PDP-6, IBM's OS 360 MFT, and Multics. Multics would heavily influence the development of Unix, a powerful multi-user, multitasking operating system whose DNA can be found in virtually every modern operating system. Fast forward a decade, and the growing demand for multitasking, coupled with its migration from the mainframe world to smaller systems, encouraged mainline CPU manufacturers to explore adding multitasking support to their processors, bringing the concept to the rapidly growing personal computing market. In a traditional single-process environment, the program being executed generally has full control of the CPU and its resources. It can access all memory and external hardware available to it. Because of this total control, if a program has to wait for input, it effectively wastes CPU processing power by idling in a wait loop. In addition, if a bug or poor program design triggers the CPU to execute invalid code or invokes external hardware in an improper way, a full crash of the system can occur. If an operating system is present, it also must rely on the program to safely return control back upon completion. These create issues with efficient CPU utilization, stability, and security as software grows more complex. In multitasking, CPU focus is shuffled between concurrently running processes. The management of who gets CPU focus next is regulated by the operating system. This improves processing efficiency by always giving focus to a process that will utilize the CPU. Multitasking operating systems generally employ either cooperative or preemptive multitasking strategies. Cooperative multitasking was used by many early multitasking operating systems. Whenever a process is given CPU focus by the operating system, it relies on the process itself to return control back. Similar to single-process operating systems, this becomes problematic if a process gets stuck in a loop. If the process can't return focus back to the operating system, this causes the system to become unresponsive or crash completely. Preemptive multitasking solved the stability problems of cooperative multitasking by reliably guaranteeing each process a regular period or time slice of CPU focus. This in effect isolates CPU access of a process from the rest of the system. If a process crashes or gets stuck, it has no effect on CPU time slice access to the operating system or other processes. Preemptive multitasking also allows an operating system to seamlessly transfer focus to processes that will utilize the CPU while another process waits for external I/O such as network devices, drives, or human interface devices. Because of its efficiency and stability, almost every modern operating system utilizes preemptive multitasking. In order to juggle multiple processes concurrently, they all need to be in memory at the same time. With the CPU constantly bouncing from program to program within memory, a mechanism for managing the memory for the processes is needed. We also need a way to prevent a process from using memory allocated to another process, but also allow them to communicate with each other safely. The solution to this is a layer of hardware dedicated to the task in between the CPU and RAM called a Memory Management Unit, or MMU. While MMU implementation varies by architecture, a common feature of all MMUs is memory protection. When a process's executable code is loaded into memory, additional memory for stack and data use are typically allocated to it. This allocated chunk of memory is said to be owned by the process. The boundaries of this memory are recorded and managed by the MMU. forming part of its protection rules. Some MMUs can also track access permissions assigned to regions of memory, limiting data or code execution access. If a process attempts to access memory outside of the protection rules, a hardware fault is triggered, causing the operating system to abnormally terminate the offending process. Memory protection is a critical mechanism of multitasking and effectively quarantines a program from the rest of the system's resources. This also secures the system from malicious or failing code as well as protect the system's overall stability. On some MMUs, the concept of memory access privileging is incorporated into memory management. With privileging, memory access outside of what's owned by a process is allowed but is restricted by a trust system. By assigning levels of privilege to regions of memory, it becomes impossible for a process to access code or data above its own privilege level. This creates a trust mechanism in which less trusted, lower privileged code cannot tamper with more trusted, critical code or memory. An operating system's core, known as its kernel, is initially loaded into memory at the highest level of privilege, giving it total control of the system. When a program is loaded into memory, the kernel assigns a lower privilege level to it. Because lower privileged code cannot directly access the higher privileged code of the operating system, a safe privilege bridging mechanism known as a call gate is used to allow highly controlled access to the operating system. The operating system now becomes both the gatekeeper and arbitrator of the system via call gates to lower privileged processes. The interface code contained within a call gate is known as the operating system's application programming interface, or API. APIs not only secure a system but also provide a unified, generalized model for programs to access system resources. Known as abstraction, APIs secure and hide the underlying complexity of system resources to programs, forming a powerful component of all modern operating systems. Some MMU designs also offer a mechanism known as virtual memory. Virtual memory is a memory management technique that provides an abstraction layer of the storage resources available on a system. Virtual memory isn't a specific requirement of multitasking, but it generally enhances its effectiveness. While virtual memory comes in various implementations, they all fundamentally function by mapping memory access from logical locations to physical ones. When program code is loaded into memory, its ultimate physical location in RAM is unpredictable. This makes writing code problematic if we want to directly reference memory, as the addresses referenced in our code will become invalid once loaded into RAM. Virtual memory solves this by allowing code to assume it starts at the very beginning of system memory. The MMU then maps all direct memory references made by the code to its true physical location in RAM seamlessly. From the code's perspective, it exists in the memory scenario it was programmed into. In reality, it may exist anywhere in physical memory. The segment memory model of the 8086 discussed in Part 2 is a crude form of virtual memory. Segmenting effectively hides the physical location of a block of memory by allowing memory references to occur relative to the top of the segment. A more sophisticated form of virtual memory, known as paging, splits memory into fixed sizes known as pages. Program memory is then logically mapped across multiple physical pages in memory. These pages can exist anywhere in memory and can even be fragmented. The MMU seamlessly pieces them together during mapping as needed. Paging is a powerful mechanism that couples tightly with other features of more advanced CPUs and will be explored further in future videos. Virtual memory also offers another advantage in the form of swapping. In swapping, idle segments or pages of memory can be swapped in and out of RAM as needed to secondary storage devices such as a hard drive. This technique allows a system to use more memory than it physically possesses and is a big part of almost every modern operating system. The mid-1980s were a milestone in the evolution of personal computers with the launch of several technologies that pioneered new ideas in computing. In January of 1983, Apple released the Lisa, one of the first personal computers to offer a graphical user interface, or GUI, in a machine aimed at both individuals and business users. Derived from research done at Xerox during the late 1970s, the revolutionary mouse-driven GUI against the desktop was the basis for Lisa's operating system. The Lisa also transitioned Apple into the use of the powerful 32-bit Motorola 68K CPU. The Lisa was plagued with dismal sales and performance issues, though it would soon be overshadowed by the release of the Apple Macintosh 1 year later. The Macintosh ran on a GUI operating system simply called Macintosh System Software that was derived from the Lisa operating system. Though the initial operating system could only run one program at a time, it supported some pseudo-multitasking features. Later versions would bring true multitasking to the Macintosh ecosystem. The Macintosh product line would eventually grow dramatically over the years with the introduction of desktop publishing in 1985 via Apple's partnership with Adobe, becoming one of IBM's major competitors up until the early 1990s. Other similar but less successful offerings of GUI-based multitasking would come from companies such as Commodore with the Amiga and Atari with its ST product line. Both also ran on variants of the Motorola 68K CPU. The Motorola 68K series of microprocessors were a workhorse of sorts during the 1980s. Its prevalence in so many systems was attributed to its powerful architecture, and it soon found itself as the x86 family's biggest competitor. What made the 68K so powerful was its early adoption of a 32-bit internal architecture. Internally, it had 8 32-bit general-purpose registers and 8 32-bit address registers, though its external bus was limited to 24 bits of addressing or about 16 megabytes of RAM. Because of its 32-bit registers, addressing memory could be done in a straightforward flat manner, with no need for memory management. Program code had no addressing limitations imposed on it. In addition to this, most of the instruction set was orthogonal, making it easier to program for. However, the 68K was not considered a true 32-bit CPU, but more of a hybrid 32-bit 16-bit processor. Both of its external buses and its two ALUs were limited to 16 bits. Despite these limitations, operating at speeds of up to 12.5 MHz, it proved to be a very capable processor. Although the 68K didn't directly support multitasking, as it lacked the ability to offer memory protection or virtual memory, several successful attempts at adding MMU features externally were made. A simple memory protection mechanism would eventually be added in later versions of the processor. Despite limited memory management, the 68K did support a simple form of privileging that made hardware-facilitated multitasking possible. The 68K always operate in one of two privilege states, the user state or the supervisor state. The supervisor state could only be triggered by an interrupt, usually caused by an exception. This supervisory state is designed to let the operating system take over control from user code upon an interrupt trigger. User mode code cannot access interrupt control instructions, leaving supervisory code to always have the final say in system operations, such as managing processes or other operating system functions. This mechanism was further aided by providing a dedicated stack register for supervisory code. Although simple, it preserved system stability by allowing supervisory code to still function even if the user code stack became corrupted from a program crash. Over the decade, production costs of the 68K would plummet, making it an excellent processor for embedded use. It became the processor of choice for many video game systems well into the early 1990s. It was also found in networking and telecom equipment, television set-top boxes, laboratory and medical instruments, and even handheld calculators. By the end of 1984, IBM took its next step forward with the release of its second generation of personal computer, the IBM PC AT. The AT was packed with several technologies that was then new in personal computers. One such advancement was the new 80-86 processor, which featured a protected memory mode. Among some of the new software developed for the AT was a project by Microsoft called Windows. With initial development beginning in 1981, Windows 1.0 made its first public debut on November 10, 1983. Running on top of MS-DOS, Windows brought a GUI platform to the PC, coupled with the support of cooperative multitasking. While it was considered a flop by modern standards and far less sophisticated than Apple's GUI, Microsoft embraced Windows as its future, setting the stage for modern GUI-based multitasking on the PC. This was the genesis of a decades-long synergistic relationship between Microsoft Windows and the Intel x86 architecture. Intel kick-started this new paradigm in computing with its next generation of processor design. The 80-86 was groundbreaking at that time in that it was the first mass-produced processor that directly supported multi-user systems with multitasking. The x86 family is known today for having one of the most elaborate MMU implementations in the microprocessor world, supporting several variants of multitasking. Support for memory protection, privileging, and several forms of virtual memory are all standard on modern x86-based processors. This remarkably powerful multitasking architecture all began with the launch of the 80-86 in 1982. Available initially in speeds up to 8 MHz, the 80-86 was up to 100% faster than the 80-86-based processor even at the same clock speed, primarily because of three key changes. The first was the elimination of multiplexing on both data and address buses. Multiplexing allows a bus to carry more data or different types of data than it physically can in one clock cycle. This is done by breaking up data transmission into smaller chunks sent over multiple clocks. While this reduces the number of physical connections needed for communication, it comes at the penalty of time. By eliminating multiplexing in an architecture and simply adding more communication lines, more data can be moved per cycle, effectively reducing processing time for most instructions. The second advancement was the moving of memory addressing control into a dedicated block of hardware. Known as its address unit, this block of hardware was in effect an MMU. Previous Intel processors used the ALU to perform addressing math, consuming clock cycles with memory addressing operations. By having a dedicated addressing unit, memory addressing math can be done independently without tying up the main processing cycle. The effect of this was faster processing time for instructions that referenced memory. The third major enhancement was an improved prefetch unit. Known as its instruction unit, the 8286 would begin decoding up to 3 instructions from its 8-byte prefetch queue. While staged in the instruction queue, instructions that could be processed with the address unit alone, such as simple memory access or the execution of jumps, would be executed in place. Because this occurs outside of the main processing loop, it significantly speeds up certain instructions. This technique is known as pipelining, and as the x86 architecture evolves, the pipeline would grow larger and more robust, facilitating pipeline execution of even larger categories of instructions. While the combination of these refinements coupled with more optimized design made the 8286 a more efficient processor, the most significant new feature of the 8286 was its inclusion of a protected memory mode. The original segmented memory model of the 8086, which was discussed in Part 2, was limited to addressing only 20 bits of memory, capping RAM capacity at 1 MB. The 8286 was capable of addressing 24 bits of memory or 16 MB of RAM, making the 8086 memory model insufficient, though in order to maintain backwards compatibility, it was supported as an operational state known as real mode. To make use of the full 16 MB, as well as facilitate multitasking, the 8286 could also operate in a state known as protected mode. In protected mode, memory was virtualized into managed segments of memory. Segments could exist anywhere in memory and be any size up to the 64 kilobyte limit. These segments of memory are tracked by the 8286's built-in MMU with an 8-byte record known as a segment descriptor. Segment descriptors not only specify the segment's location and size in physical memory, but also its purpose. A data segment, for example, could function as a memory buffer or a stack, while a code segment contains executable instructions. The in-memory availability of a segment is also tracked by the descriptor. This allows for the swapping of segments in and out of secondary storage as needed. Segment descriptors provide a security framework by allowing write protection for data segments and read protection for code segments. It also prevented data segments from executing code and code segments from accessing memory outside of defined descriptor boundaries. Segments were also secured by the implementation of a 4-level privilege system. Each segment was assigned a privilege level, restricting access to other segments of equal or less privilege levels, forcing the use of higher privileged operating system code for access to system resources. If segment rules are violated, an exception occurs, forcing an interrupt trigger of operating system code. The 8286's MMU tracked all segments in 2 tables: the Global Descriptor Table, or GDT, which provided persistent system-wide segment access, and the Local Descriptor Table, or LDT, which offered a dynamically loadable segment table for individual process use. Each table could track 8,192 segments. With a maximum segment size of 64 kilobytes, both tables combined could potentially address up to 1 GB of virtual memory. Aside from storing general use memory segments, the Global Descriptor Table had several other functions. It stored the segments that contained local descriptor tables intended for use by various processes. It also stored call gate descriptors, which point to higher privileged segments, usually containing operating system code that can bridge functionality to lower privileged processes. And finally, it contained segment references to a memory structure known as a task state segment. The task state segment is used by the CPU to manage task switching and multitasking. When control is transferred between processes in multitasking, a mechanism is needed to store the state of the CPU for the last process so that it can be restored seamlessly when CPU focus is returned to it. This information was stored in the task state segment, as well as other task-specific permissions such as direct external bus access. The interrupt structure of protected mode is very different from real mode in that it has a table of its own, known as the interrupt descriptor table. The interrupt descriptor table, or IDT, pointed to code segments that directly mapped to interrupt triggers. Operating at the highest privilege, code segments in the IDT were responsible for responding to memory protection exceptions, hardware requests, and task switching via a dedicated code segment known as a task gate. While task gates, in combination with task state segments, were designed to offer hardware-level task switching to the operating system, in practice it was seldom used due to its lack of flexibility and performance issues. While the advanced ideas of the 8286's protected mode paradigm would eventually evolve into the standard for modern PC operating systems, when it was launched, it suffered from several flaws that had hindered its adoption. Protected mode was dramatically incompatible with existing 8086 software, making it difficult to adopt. This was further exacerbated by its inability to switch back to real mode from protected mode without resetting. Protected mode also came with a slight performance penalty due to the privileging mechanism, and while it allowed for accessing to more memory overall, it could only work with 4 simultaneous 64 kilobyte segments at once or 256 kilobytes, offering no real advantage over real mode. The lack of backwards compatibility led Bill Gates to famously refer to the 8286 as a brain-dead chip, since the new Microsoft Windows environment would not be able to run multiple MS-DOS applications on it, defeating the point of multitasking. The flaws of the 8286 would eventually be addressed with a more refined protected mode, making its way into Intel's next generation of CPUs, solidifying its importance in bringing multitasking to the modern PC.